Olá, boa tarde.
Som. So, good afternoon, everybody. Welcome to this afternoon session. My name is Alexandre. I'll be the chairperson for this afternoon. And the first talk is going to be given by Lucas Foppa from the Fritz Haber. And his talk is titled AI-Guided Workflows for Materials Design. So, Lucas.
Thanks a lot for the introduction. And I would like to start by thanking Mariana and Luana for the invitation to come here. So it's not my first time in Brazil, but it's my first time in Campinas. So I'm very happy to be here and also looking forward to the discussions and already had a nice time here. Before starting to with the scientific part and explaining what we have been doing in my group in the Fritz Haber Institute, I would like to say a few words about myself. So even though I have an affiliation from the Fritz Haber Institute, and I think more than one person talked to me in English in this conference, I'm from Brazil. So I'm born and raised in outside Porto Alegre, close to this city that you might have heard of, Bento Gonçalves. And I always have these slides here because people, especially from Europe, often don't know that we have a wine yard region in south of Brazil. So that's where I come from. So here you see the vineyards, and even like this city that whose entrance is this barrow. So you go through the barrow to enter the city. Well, I moved to Porto Alegre for my studies. And in the URGS, or Federal University of Rio Grande do Sul, I studied chemical engineering and finished in 2013. And already at that time, I did half of my studies in France. There was an exchange program with some French schools, so I did also part of my undergrad studies there. After that, I moved back to Porto Alegre and did a master's in chemistry. So I was working with Professor Jairton do Ponte at University of Federal Rio Grande do Sul. And after my master's, so here, funny thing is that I was doing experimental chemistry, working heterogeneous catalysis in the lab. But this was not such a good idea. I didn't realize back then there was a theoretician. So I moved to Zurich afterwards to do my PhD in theoretical chemistry, in computational chemistry. So I was modeling surfaces and nanoparticles, also for chemistry. And after, at the end of my PhD, I wrote a Swiss National Science Foundation fellowship to come to Berlin to learn about AI, materials science, and chemistry. And here I would like to highlight that Mariana was a very important piece of this step here, because she was my connection, and she kindly introduced me to the people at the Fritz with whom I wrote this proposal, which was successful. And so since 2019, I'm there. I did my postdoc, and then in 2021, I became a group leader of a group that is called Ab initio and AI Methods for Heterogeneous Catalysis. So in my group, we are developing concepts and AI methodologies and applying them to experimental material science and computational material science with a special focus in catalysis. So in the presentation today, I would like to, I'm not going to talk too much about the chemistry, but I would like to highlight a bit how AI-guided workflows can be used for the discovery or the design of new materials. And I hope I can resonate with some of the concepts and presentations that were given here at this conference. Okay, so when we talk about materials discovery or materials design, so the problem we have in hand is that if we imagine the number of elements that we have in the periodic table and how these elements can be arranged in space, we can easily conclude that the number of possible materials is practically infinite. And the number of useful materials out of this immense pool of materials is very low, right? So if you think about catalysis or other applications, only a handful of materials will be useful for a certain application. So we have to navigate in this space efficiently in order to design new materials that we need for energy conversion, for instance, or energy harvesting. So how can we do that? So one of the way AI has been used in material science is to create a model of some material property, and that can be used to estimate this property and guide us this search in this immense material space. So the way we have been doing that is the following. We have a certain material space and a certain Y here, which is a property of interest. So you can think about this as a band gap or the compressibility of a material and so on. And we have this material space where we have many unknown values. So we don't know the property for most of the materials in this space, but we know few of these values, so the labels of our model. So we use this information of these few known values to create a data set, which we are going to use to train a model. So in here, this yx is a known ground truth, so the function we are trying to model in terms of a descriptor, which you can think of as a vector of physical parameters that will encode the properties of the material, for instance, the composition or the structure and so on. And here we are going to create this fx, which is the AI fit to these few known data. And so if we do a good job, we have some good approximation for this function, and then we can use this function to estimate the property for this material space. So how do we know if we have a successful model in general? So we often look at the model performance in average. So you have seen several times today and yesterday that we often look at the root mean square error or mean absolute error to understand if a model is useful or not. However, in the context of materials discovery, good average performance, good performance in average might not translate to a good description of promising materials, because these promising materials might be very few compared to the bulk of materials that we have in this material space. So realizing this issue, the community has increasingly shifted from what we call prediction to action. So instead of having a static model that we can use to make predictions, we are going to now have a workflow where we have an iteratively modeling and data acquisition approach to identify materials with desired properties. So here I'm talking about approaches such as black box optimization for materials properties, which means, so we call it black box because of this function here that is a node, so it's a black box function. And so this is the type of approach we're going to use in order to, at the same time, model and improve the model and the training data. So how does this work? We are going to have the data set at which we train this, with which we train this AI model, but then we are going to use this model to rank these materials in this material space according to a so-called acquisition function that was mentioned by Christian today. So this is a function that is informed by the AI model, especially it's informed by the predictions and the uncertainties of the model in order to choose the next materials that should be investigated. For instance, by a calculation or by an experiment if you want. So for instance, here in this material space, imagine that this is the point that we have the highest value of acquisition function. This means that we are going to acquire the label for this specific material, add to the data set, and retrain the model. So this is going to go over and over many iterations until we hopefully reach a certain maximum of a property that we are interested on. Okay, so this is kind of the concept of this black box optimization for the discovery or the design of new materials. So here I would like also to highlight that when we talk about material discovery, so there is some criticism about this term because we are not discovering new materials, we are discovering materials for which we don't have the properties, yeah, because we need to start with a list of materials that we consider in the analysis. Okay, so in this context, there are new questions that come compared to the questions that we have in a static picture. So first, now the performance, the first point I want to make in the presentation is to show how this performance now depends not only on the model and its uncertainty estimates, but this will depend also in the acquisition strategy, so in this acquisition function. And I will illustrate this with one example. Then I would like, in the second part of the presentation, I would like to discuss how, give some discussion about this descriptor. So we often use a vector that contains information about the materials as an input to the model, but we want to learn something about the chemistry or physics behind this property. So how can we use a workflow that is based on a descriptor that is interpretable? And here we are going to discuss symbolic regression approach to obtain this descriptor, so which is going to be an analytical function. Okay, so let's start with the first point here. And I would like to illustrate this with this tutorial problem, which is the identification of perovskites with high bulk modulus. So our target of interest here is going to be the bulk modulus. There is a property that measures, correlates with the compressibility of the material, so the resistance towards compressibility. And here we are going to be looking at cubic perovskites, which are single perovskites of this type here, ABO3, and double perovskites that have this general formula. So this is all done with calculations. We are using DFT PB-SOL, so it's a GGA exchange correlation functional for calculating this materials property. And we start with an initial data set of 814 materials, and then we have a material space of more than 30,000 materials. So we want to find among these 30,000 materials the perovskite with the highest bulk modulus possible. And we want to do this very efficiently. So we don't want to run a lot of calculations. We want to run few calculations and identify already good candidates. Okay, so we're going to be looking at two very popular machine learning models that were also mentioned already here, Gaussian process and random forest. And here, as a descriptor, we're going to use a vector that contains elemental properties of the A and B elements that will enter in this composition of these materials. So here, we have a fixed structure, so the descriptor contains only the chemical composition of the materials. So these are, for instance, radii, electronegativity, ionization potential, and so on. Okay, now I would like to discuss two acquisition functions. First one is what we call pure exploitation, XT, and second one is the very popular expected improvement. So in case you're not familiar with these acquisition functions, I give you some intuitive explanation about them. So the first one, so here first, by using this nomenclature from the reinforcement learning community, we define a reward, which in the case of black box optimization is going to be the quantity that we want to maximize at each iteration. So here, our reward is the maximum bulk modulus observed so far. So by using this reward, we aim at always selecting materials with higher and higher bulk modulus. So what this first acquisition function, pure exploitation, does is to look at the predictions, so here in blue, of this model across the descriptor space, or all the material that are the candidates, and we'll select simply the highest value, aiming at finding materials with very high bulk modulus. So this is the first acquisition function. So this acquisition function will only use the prediction of the model. So it does not use the uncertainty estimate of the prediction. Now, the second acquisition function, the expect improvement, will use both the predictions and uncertainties. So here, I hope you can see from the back, but here there's a gray shaded area in this plot, which reflects the uncertainty of the model prediction. So this acquisition function will look at the expectation value of the improvement with respect to the best material known so far. That's what the expected improvement will evaluate. So in this diagram here, this would correspond to this area here. So if we have this prediction, the expected improvement will look at the improvement that we expect from this point. So here you see that this acquisition, so this is the value of the acquisition function for this toy example. So this will not favor the acquisition of data very close to the known values because the uncertainty is low there, but it will also steer the acquisition of data in unseen parts of the material space where the uncertainty is higher. Yeah? So this is the intuition behind expect improvement. Okay, so here, I mean, just to talk about nomenclature, so the predictions, when we use the predictions to get the new data, we are exploiting the model, and when we use the uncertainties to go to areas of the material space that we have not seen yet, we are exploring the material space. Okay, so in total, combining these two AI models with two acquisition functions, we have 4 different methods that are listed here. And that's what we are going to be looking at. Okay, so if we look at the performance of these two models as a function of the dataset size for using the initial dataset, this is what we have. So this is the mean squared error. And here, the size of the training dataset. And here, we are using we are sampling with replacement the dataset to obtain the training data and evaluating the performance in the remaining part of the data. So here we see that first, the two models are learning with data, which is what we expect. And second, we see that the performance are very similar, with random forest being slightly better than Gaussian process. So from these results, we would expect that they perform in a similar way in the optimization, maybe with random forests having some advantage because the predictive performance is a bit higher. However, when we run the experiment, this is not exactly what we see. So here, I'm showing you the maximum value of bulk modules as a function of iterations in which we are running this black box optimization. So you see that all the curves start from this value here. And each of these colors represent one of the methods, so one of the models with one of the acquisition functions. And here we also have this black curve which reflects the random sampling. So if we just randomly select materials from the material space, this is what we would get. And here we see that Gaussian process with expect improvement is the method that provides faster these materials with high bulk modulus. So the improvement you see here, it's significant compared to what we had initially. So so here I would also like to highlight that Gaussian process with pure exploitation did not find any material with high bulk modulus compared to the one in the initial data set. So meaning that the exploration, so the uncertainties are really crucial in this case to obtain these new materials with higher bulk modulus. Okay, so what is the conclusion here? So the predicted performance evaluated on the initial dataset does not always reflect the performance in black box optimization because we also have an uncertainty estimate component there, and the acquisition function also matters. So this is what we get from this simple experiment. So both the model and the acquisition strategy matter. Yeah. We have been looking also ways to estimate the performance based on the initial dataset, but we find it very challenging to tell something about which combination will be the best one in a certain problem. Last thing I wanted to mention about this example is if we look at the performance for the discovered materials, we see very different numbers compared to the performance that we estimated using the initial dataset. So here I show you the histogram number of counts as a function here of the bulk modulus value. So this is the initial dataset in gray, and these are the discovered materials. Obviously, they have very high values of bulk modulus. And here, these are the curves you've seen before. And now I am also plotting the performance of the models that were obtained with the initial dataset for the discovered materials. And you see here that the performance is significantly worse than the performance that we obtain only by randomly selecting the materials in this initial dataset. So meaning that the predicted performance estimated on the initial dataset can be over-optimistic with respect to the performance that we have when we actually use this model to obtain or select new materials. Okay, so now moving to the second part of the presentation, I would like to discuss like this something about the descriptor. So far we have a vector that we feed it to the machine learning model, and then we interpolate it in this space. So this means that we often have to make some extra work to think about this descriptor and have an appropriate description, otherwise our optimization will not work. However, can we do this automatically? Okay, so this is the second example where I will illustrate how we can use this symbolic regression machinery to get this descriptor. And here, this is a more exciting example where we're going to be looking at, we are going to identify acid-stable oxides for the water splitting reaction. So in case you're not familiar with the water splitting reaction, it's a crucial reaction for chemical energy conversion because we can use energy coming from a renewable source to split water, and then we can use the hydrogen in a fuel cell later on. And the sluggish step of this reaction, so there are two parts, so the hydrogen evolution reaction and the oxygen evolution reaction, and this is the most challenging part here because of the sluggish kinetics of this reaction. So there's a lot of research on materials for enabling this efficient oxygen evolution reaction. One of the classes of materials that is very popular for this, and also that is promising because of the stability, is oxides. And so here we are going to be looking at a target property that reflects the stability of oxides under oxygen evolution reaction conditions. And here I want to mention that there's a lot of work on the surface reactivity of these materials because it's a catalytic reaction. However, many of the materials that can be catalytically active, they might just dissolve under acid conditions. So the stability is an often overlooked factor in this materials design problem. Okay, so here our target is going to be the decomposition energy at these conditions, and our material space is going to be binary and ternary oxides. So a few words why this is a challenging target and why we need black box optimization or AI here. So to evaluate this property computationally, we use the so-called Purbe analysis. So this Purbe analysis is an analysis that generates a phase diagram where the coordinates are the applied potential and the pH, that tells us which are the stable phases under certain conditions that are relevant for electrochemistry. So in order to evaluate the diagram, for instance, for this oxide here, we need to consider computationally, for instance, the energies, formation energies of all the oxides, intermetallics, and hydrides that can exist in this diagram. So this is really a time-consuming and resource-consuming property to be evaluated. So for instance here, this green area here is the region where this delta G Purbe is 0, so meaning that this compound is stable. And this star here represents the conditions we are going to be looking at of the acid-based OER. Yeah, there are acid-base and basic conditions also. Here we are only focusing on the acid-base. And yeah, and as you might know, oxides are not well described by GGA, so we need to use a method that is better than GGA. And here we are going to be using DFT HSE06 calculations that provide a much better description of oxides compared to GGA. So here, I mean, as was mentioned by Christian in his talk this morning, we are using this very efficient implementation in FHIMs that allow us to like do all of these calculations with reasonable accuracy and speed. Okay, so I discussed about the target. Now let's go to the AI part. So here we are going to be using a symbolic regression approach that is called CISO. So some of you might have heard about this technique before. And I will briefly explain how the concept of this method. So the CISO stands for Shared Independent Screening and Specifying Operator, and this is a symbolic regression approach that combines feature construction with compressed sensing that was developed at our institute a couple of years ago. So the first step in the CISO approach is the selection of the input parameters that we refer to as primary features. So these are physical parameters that reflect possible processes that are controlling the target of interest. And here I would like to highlight that it's important to offer a lot of parameters and let the model choose which are the relevant parameters, because we often initially don't know which are the relevant processes. So we want to offer a lot of primary features. So this is the first step. And then once we have this list of features, we are going to apply, so this primary feature space, we're going to apply unary and binary mathematical operators to these features and combine them. And these combinations can be very nonlinear, and they will importantly capture the interaction between features, because some of the operators will combine different features. For instance, differences or absolute value of difference and so on. And here I would like to note because Professor Fazio made me this this remark when I presented this last time here, that we are taking into account the units of the primary features when we do this construction. So we don't allow, for instance, a length to be combined with an energy according to the difference operator. So we are really taking into account the units of these features in order to construct these expressions. Okay, we can construct many of these expressions. And then we apply a technique called compress sensing in order to select the few features or few expressions that combined by weighting coefficients will best correlate with the target of interest. And here there are two steps. So the shared independent screening step, where we look at the correlations between these expressions and the target. And then we select these few features that best correlate with the target. And we do the same for the residual of the previously identified model. And then in a second step, we're going to apply our sparsifying operator, which is nothing more than a L0 optimization, where we look at, we select only few features out of this sub-selected space that we generate by the SIS approach. So at the end of this analysis, we're going to have a descriptor and a model. So descriptor is this DI expressions. They are part of a vector that we call descriptor. And these are the CIs, are the fitted coefficients that are going to be really chosen to minimize the root mean square error. Okay, so here you see that this expression looks very linear, but remember that we have applied nonlinear operations to create these expressions. So the nonlinearity is inside this DI, these analytical expressions. Okay, so these descriptors here can be used to create what we call materials property maps that arrange the materials according to the performance. And so here, for instance, you will see that this is the color reflects the predicted value of the target, and these data points the training set. So this is the type of low-dimensional representation that we get with CISO. Final thing I want to say here is that the number of candidate features or expressions that we generate by applying these mathematical operators is really huge. So we're talking about billions or even trillions of expressions. And in the end of the analysis, we're going to end up with very few of these expressions. So the dimensionality, this D of this descriptor, is going to be low, typically 2 or 3. And this also means that from all of the primary features that we offered initially in the analysis, we only have few of them that are going to be showing up in the descriptor expression. So this is how we do feature selection and understand which are the most important features. Okay, now coming back to our problem. So we have now the target, the CISO approach, and here I give you like some the primary features that we use in this problem. We are using 14 physical descriptive parameters that depend on the composition of the oxides. And these are, again, atomic radii, oxidation states, and so on. So very simple compositional parameters. Okay, now if we train the CISO model with the initial data set here, we obtain such map. And here we can discuss the coordinates of these maps because they are analytical expressions. And we can specifically understand which are the key parameters that show up there. And here we have, for instance, this sigma here, which is the standard deviation of the oxidation states that we have in the material. We have the radii of certain orbitals, the number of vacant orbitals, and the radii, covalent radii of some of these components. So this means that the distribution of oxidation states in the oxide is correlated with the stability under electrochemical conditions. And also the size of the cations that enter there. It's important to determine the stability of the material under electrochemical conditions. Okay, so this is the training set here, and this is the map. So here you see that this goes from very negative values to more positive values. So this is the delta G per B, our target. Okay, very good. So we have an initial map, but how can we use now this map or this model in order to have this sequential learning? So here, we're going to set up a reward that is the number of stable materials. So we want this value of this target to be lower than 0, actually. Here we have like we consider a slightly higher threshold to take into account that also we have calculations that have some errors, right? Even though we are using hybrid functional. So this is the threshold. So this is the acquisition function we are going to use here. It's called probability of feasibility. And here, this acquisition function will take into account the prediction and the uncertainty of the model. So we're going to integrate this, if you want, this area here, and we are going to be looking at to which extent, so what's the probability of a material to have the value of the target lower than a certain threshold. Okay, so this looks fine, but we don't have an uncertainty of the CISO model. We just have this map that what was trained with the whole data set. How can we obtain uncertainties? And here we have done some work using an ensemble approach to get this uncertainty. So a few details on the methods that we have developed for that. So the first the first method that we use to create an ensemble of CISO models and extract the uncertainty out of this ensemble is the standard bagging approach. And some of you might have heard about that, but if not, so in a simplified way, so we first start with this data set, and we use a bootstrap approach, which means that we sample with replacement from this data set to create different data sets that are slightly different from the initial data set. Then we use each of these data sets to train a different model. So we have an ensemble of K models here. Each of these models will give a prediction for a new data point. Yeah. And then we look at the distribution of these predictions. And from this, we extract two things. First, the mean prediction, so this value here. So we just look at the mean value of all the predictions. And then we look at the standard deviation of these predictions in order to get an idea of the uncertainty estimate. So this R sigma is how we extract some measure of the uncertainty of the prediction. So this is the first approach. So it's quite standard. That's the bagging approach, which comes from bootstrap plus aggregating, which is the step where we combine the predictions. In addition to this standard method, we also looked at other methods that will introduce variability in the model or in the features that enter in the model. So the first of this, the second approach is the bagging with multiple model complexities. So now we are going to create different data sets using sampling with replacement, but then we are going to train different models with different complexity for each of the data set. And this can be, for instance, models with different number of dimensions in the descriptor. For instance, slightly higher and slightly lower than the optimal dimension that we identified by cross-validation actually here. So this is the second approach, and we again use this distribution to extract the prediction, the mean prediction and the uncertainty, so the standard deviation, for instance. Third approach is what we call bagging with Monte Carlo dropout of primary features. Now we again are going to have the bootstrap procedure here, but then we are going to randomly drop part of the primary features to train the model. And here we are going to be doing a dropout of 20% of the features. And yeah, of course, this can be adjusted. And then we obtain these K different models. And we can, again, calculate mean predictions and standard deviations to get uncertainties, right? So here we are introducing variability both in terms of the data set in which the models are created, but also in the features that enter in the model. Okay, so how do we know which is the best approach? So I show you how we evaluate the accuracy of that. So first, we look at absolute prediction errors. And so this is the absolute error, and this violin plots here, they reflect so you have here the box plot with these different metrics of the distribution of errors, but the violin also reflects the number of systems. So the width of this violin reflects the number of systems at certain value of error. Yeah, so this is a more complete description compared to the box plot. And so if we have only one single CISO model, so no ensemble at all, we have this distribution of errors. Now, for the bagging approach, we see that we have a very similar distribution of errors. So this doesn't change significantly the prediction of the mean prediction of the model. Now, with these two different approaches here, we see that even though the mean value of the error is similar, we don't have the very high errors that we observed with the single CISO model or with the standard bagging approach. So this means that the proposed ensemble approaches are mitigating these high errors here that you see here that you don't see here. Yeah. So we have some indication that the ensemble's prediction ability is better than the single model. Now, what about the uncertainty estimates? To say something about that, we looked at what we call miscalibration score. So this quantity that we denote by Z is actually the ratio between the absolute error and the standard deviation of the model prediction. So this means that if this value is equal to 1, we have what we would call a well-calibrated model where the error corresponds to the standard deviation of the prediction. If we have a higher value, we have an overconfident model. and if we are below this value, we have underconfident. And this overconfidence is a problem for our black box optimization, because if we use the uncertainty to steer the acquisition of data in new parts of the material space, this will not be efficient if the uncertainty is lower than what we should expect in those regions, right? So that's problematic. Okay, so this is the bagging approach. We have this distribution of Z values here. So we have, it's quite overconfident, this model. And now if we apply these different ensemble approaches, we have a significant improvement, especially for this case, where we have this mean value of Z going down, and the distribution is also narrower than this distribution here. So this means that the use of the primary feature dropout mitigates this overconfidence issue that we have using the standard bagging approach. Okay, so now we are happy with this approach, so we can apply it to the actually sequential learning. So that's what we do next. So we use this CISO ensemble with primary feature dropout to select new materials with the probability of feasibility acquisition function, and this is the result. Here we look at the number of oxides discovered, so stable oxides, as a function of the number of iterations. So this red curve here is what we obtain by using the CISO model with the predictions and uncertainties. And here we have the random sampling. So if we just sample randomly a material from this space, this is what we get. So we see that we don't identify this is not efficient. But by using the model, we improve this efficiently, and we discover 12 stable oxides out of these 1,000 candidates in only 30 iterations. Okay, so now we can also visualize these results in the CISO map. So here I show, so this is the map you've seen before. Here I show you the region of interest. And here this is the training data. So now in white here, I show the materials that are in this material space, so the candidate materials, and we see that they are mostly concentrated here. So that's why a random sampling is not efficient, because if we randomly sample, we are gonna mostly pick materials from this region here. So this is what we showed here in these gray circles. Now, if we use the probability of feasibility and that we obtain using the CISO model, that's the materials that we are going to be sampling. So, and from this map, we see that most of the materials that are identified as stable, they were correctly predicted by the initial CISO model. So we actually didn't need active learning or sequential learning to discover them. However, some materials that lie in the unstable region turned out to be stable. So this means that the model was also improved by this iterative data acquisition, which is something that we, of course, desire. So the CISO selection of data points helped us to improve the description in the regions of the material space that we care about. Okay, very good. So now this is the summary. We have, I showed you here how both AI model and acquisition function will matter in this black box optimization of materials property, not only the model. Now, we have proposed this ensemble of CISO models for obtaining, estimating the prediction uncertainty of the CISO models, which was non-existing before. We only had a map. And finally, we have applied this CISO guided workflow to intelligently select the materials with desirable properties. So now we can do expensive experiments or calculation because we intelligently select the materials for which we perform the simulations or experiments. So this is why we believe that this is a promising approach for materials discovery. Okay, so now as an outlook, I would like to mention some, if I have time, some different approaches that we are going to be are using in the group also to actually identify outstanding materials. And we have been looking more recently at focus models of materials properties, meaning that these are not global models, but they will focus in specific regions of the material space. So why do we care about this? So first, in a typical case, most of the training data correspond to low performance. So if you're looking, most of the materials we know, they don't work for the property, for the application that we want. So and second, there are different mechanisms for different subsets of materials. So we might have the risk that we have, so if we have a performance in terms of a descriptor, we might have a lot of data points here, and if we fit a model using the whole data set, we might be mismodeling the materials we care about. So we have been thinking how we can use focus models in order to get description only of the materials portion of the material space that we care about. So here I give you some references, but we have been using a technique called subgroup discovery that allow us to get focus descriptions of materials that don't target the whole material space. And here, this is a semi-supervised, so it's a supervised technique where we look at the materials or subgroups of materials that are outstanding with respect to a target of interest. And yeah, please approach me if you're interested by this type of approach, but we have some applications, and if you trust me from this cartoon, we do get the description of these models, and we can fit a regression model only in subspaces of this material, and for some applications in catalysis, this has been shown to be very useful. Okay, now I would like to acknowledge our group in Berlin. So first, Matthias Schäffler, that has been supporting this research over the years. My postdoc, Akil Nair, who has done this CISO ensemble approach and the active learning. Here is the remaining part of the group, so Serjani, who joined the group recently in Berlin, and our collaboration in Monash University for this black box optimization problem. And here, this is Herzain, a postdoc in our group that has now has an industrial job, but he had been working on the subgroup discovery approaches. Finally, I want to advertise this conference if you're interested in catalysis. So it's a Faraday conference that is taking place next year in London. So it's a conference that will discuss advances in heterogeneous catalysis and modeling, specifically AI-driven modeling of catalysis. So yeah, if you're interested, please approach me. We can discuss that. And finally, I leave you here with the summary and some references. And here, I would just like to point out to this roadmap paper on Archive that discusses a lot of these advancements that we have in the FHIM software package that were also mentioned by Christian. So it's a good point to start in case you didn't use this code before. Yeah, and I'll be very happy to take your questions. Thanks a lot for the invitation again.
Thank you very much. Questions? So before it gets there, so I'll start with a question. Yeah, so actually, maybe I missed this, but so at the end of the day, what are the most important features that you actually find after running the CISO on your system?
In this specific case, we have offered 14 features, and we see here that the model that we obtain only contains few of the features. So here, yeah, in this slide. So we start with 14 features, and then we create these expressions, and finally the expressions contain 4 of these features. So you can, I mean, I discussed what they could mean, right? But I think we have to also keep in mind that this is a correlation. So the relationship between the features and the property might be indirect. So, but I think from our experience, we can learn significantly if we look at these features out of a list of offered features. So I don't know if this answers your question, but for the fact that we have the standard deviation of oxidation states here makes sense because when you have different oxidation states, you have more decomposition pathways for the oxide. So this makes us make the material more likely to be unstable. For instance, this is the kind of way you can rationalize that.
Hello, Lucas. Thank you for your excellent talk. And I have one question about the active learning using CISO. And my first question is, during the active steps, the model changes. Yes.
Mm-hmm. Yeah.
And my question is, how the features, thinking about explainability of the model, how the features changes during the active learning steps. There are some conservation of the principal features that they describe this property.
Yeah, that's an excellent question, and we also are curious about that. So in this specific case, what I can tell you is that we don't see the coordinates of this map changing significantly with the number of iterations. And also from the results I showed here, you see that the initial model in this case was quite good actually. So this means that we had the correct features or the features that capture the underlying physics. However, in general, this could change significantly as we evolve in active learning. So I think it makes sense that this changes because you're improving the description in one of the regions of this space. And for that region, the physical processes might be different compared to other regions. So it's a fair point. Here we don't see a significant change, but in general it could well be the case.
Okay, thank you.
Yes.
Thank you, Lucas, for the great talk. So I just want to hear your thoughts on what are the frontiers in this area of active learning in 3 points. The first one being when you have high dimension problems, so where you may want to optimize different areas. The second one is multiple outputs. There's a whole range of challenges there. And also Q-batch sampling, where you want to get more than one candidate at a time.
Yeah, excellent points. So for the first one, well, CISO is inherently a dimensionality reduction technique because we are going to start with a very high dimensional space of features, and you're going to end up with less features. So in this case, like you went for 14 and 4. So this is a great advantage compared to Gaussian process, for instance, or kernel methods, as was mentioned also by Mariana and others here. So this is the first point. So this, I think it's really great that we can have this inbuilt in the CISO model. Second, for the multi-objective, so we are be looking at multi-objective optimization because indeed we don't want necessarily only one type of property. For instance, here, this is the stability. But if a material is catalytically dead, it doesn't matter that it's a rock and it will not dissolve under acid, right? So there are different approaches for that, and we have been looking at the Pareto front of solutions that will have a compromise between conflicting objectives, for instance. So this is, I think all of this machinery can be adapted. It's just that the acquisition function will have to be rewritten, but I think it's quite straightforward. And for the last point, indeed, when we have a calculation, for instance, you can submit more than one calculations, right? Or an experiment, if you have a parallel reactors, for instance, in chemistry, you can submit more of them. So there are established methods actually to choose this batch of materials efficiently, right? So if you don't necessarily take the ones with the high acquisition function, because they might be very similar, but you can create spikes in this material space and then favor the diversity in these batches. So there is a whole literature that deals with that. So I think we don't have to reinvent the wheel, only bring these concepts that belong to data science and informatics to our material science field.
And you're looking at these types of problems or just looking ahead?
Actually here, I can tell you that if you look at the property calculated by HSE, there is some correlation with the property calculated by PBE also. So in addition to multi-objective, we are looking at multi-fidelity because we have more GGA data than HSE, and we want to make sure that we use this information when we select the materials, right? Yeah.
Great, thank you.
So if there are no further questions, so let's thank Lucas again.
Thank you.
And I would like to invite the next speaker, Felipe, to set up his talk. I always get Felipe's surname wrong. I guess everybody does, right? Yeah. So the next speaker is Felipe David Crasto de Lima. He's here from Ilum.
Okay.
So I have to read here. And the title of his talk is Computing Defect-Driven Topological Transistors in Two-Dimensional Materials.
So thank you, the organizers, to bring all those peoples together and for the opportunity to show here part of my recent work. So let me just get this here. So I talk a bit, I will deviate a bit from the last two talks that was focused on machine learning, and I will talk a bit more on some topological transition in two-dimensional systems. And here, yesterday, Gabriel set some grounds for the theoretical group of researchers here in the CNPEM Center. So we'll talk just to complement in this new lab that we have here, but this is an educational lab, which is the Ilum School of Science. And we have, among other faculties that are focused in math, biology, but we have these 4 peoples that are working in theoretical simulation, data science, but in material science, which is James, which I think everyone knows, and Daniel, which is here on the conference there, Adalberto Fazio, Professor Adalberto Fazio, and me. And particularly, I have more strong collaboration with Professor Fazio, which we stood, among other things, some of these topological materials, emergent quasi-particles in two-dimensional system, and some other things. And our group, I didn't get a picture of everyone, but currently has a doctorate, Pedro Sofia, which is also here on the watching us, and 2 postdocs. One is leaving, one it's getting in the next weeks, and some undergrad students that are developing different projects in the group. And we have some recent theoretical collaborators. Professor Hiroki and Carlos are here also, which is good, and Professor Caio Lebenkoff is in the Federal University of Rio de Janeiro. And one point that is important in our work, it's the experimental collaboration, which help us guide the direction that we are going to follow. So I would like to highlight Joaquim Mendes, that are from Federal University of Viçosa, and João Batista and Murilo Santiago, that are working here in the campus. But also Hiroki and me has a collaboration with a group in Canada, which focus more in molecular self-assembly. And of course, all this works is financially by a thematic research project in FAPESP that are coordinated by Professor Gustavo Dalpian, and the INCT Materials Informatics from Professor Fazio. So what are these topological phases that I'm going to talk about? And I will, so here is something that it's more familiar to everyone, that there is the Hall effect. So when you introduce a magnetic field in a two-dimensional system, you can see a charge separation in different surfaces. But if you have strong enough a magnetic field, we can actually see a quantized states in the system interface, and we can have the same system, same idea without the external magnetic field, which is the quantum anomaly Hall effect. But we can also have a analogous system without any kind of magnetization, where this spin separation now comes from the spin-orb coupling effect, and there is this spin Hall effect, which is the classical version, but we can also have the quantum phenomena associated, which are the quantum spin Hall effect. In the end, in this context, there is the rise of this topology in the condensed matter. So if you look to these 2 materials in the book, we see there are some valency states and conduction states. There seems to be similar, but when you look to the geometrical phase of the wave function of the system, they are different. So actually we can, if you try to connect this material, this Hamiltonian with the other, trying to preserve a given property, in this case the energy gap of the system, we cannot do it. So at some point this property will be violated, and this is a similar problem that was already very discussed in mathematics, which is the formation and classification of a continuous surface. We cannot take a sphere to a donut without pinching a hole in the surface. So what this means in the end is that if you have an interface between materials that are in different class, what here we call some of these classes that are topologically trivial because they are connected with the vacuum, and topological non-trivial because they are not adiabatically connected with vacuum. If you have a connection between these 2 materials, we end up having metallic interface states that can no longer allow for backscattering of the charged particles. So this has a lot of interesting application, mainly in spin charge conversion and spintronic devices. So this is something that we are interested in to look at. But also, if you look back in time, we see there are a lot of devices that are interfacing with us today, like LEDs, transistors, solar cells, and so on, are developed from the capability of manipulating the effects in semiconductors. So here is just highlighting that introducing defects, we can actually manipulate charge transport, induced magnetism, and so on. And this starts in the 50s in the Bell Labs, which there are some ideas that how you can use external parameters to manipulate vacancy in the system. So this is an initial paper of Shockley. Somewhere in this paper there is the word design. So he comment about this thing. You can choose thermal gradients to manipulate the localization of vacancy. And this is a more recent work of me and Professor Hiroki, where we show that with an STM tip, you can actually create vacancies in some systems and manipulate the electronic properties. So the question that connects these two areas are, it is possible that to inducing defects on a given material that are topologically trivial, so it's connected to the sphere, you can lead to a topological transition. So you can change this sphere subspace to a donut. And this question is actually counterintuitive, because when you look to when you create vacancies in a system, if we start from a trivial phase and we are diminishing the atomic concentration, we are actually, it seems that we are going towards a more localized material or states in material, and for a perfect localized state, the topological invariant, it's always trivial. So for a perfect localized wave function that live in this material, actually this is the barrier connection, which is connected with the chair number. It's in this case essentially the position operator, and for a perfect localized wave function, this is always 0. So, but in the middle of this transition, something can happen, and that was our idea. So if you take a completely insulator semiconductor material, they have a gap in the band structure. If you puncture a hole here, remove an atom, there may be some localized states that has no dispersion, but if you puncture enough defects or remove enough atoms, there may be delocalized states, and those delocalized states, in principle, can give origin to topological phase. So this is the premise, and that's the question that we start with, and I will try to answer in the few slides. So, can vacancy interaction induce a band inversion, or can lead to a topological transition? So now we need to look to the local environment of a vacancy. So if you think in a different material geometry, and we remove an atom, what we end up with is a lot of dangling bonds in the system. So there are some localized states in this around this vacancy area. So to try to understand this, I built just a play of underground simple physics, so we can actually build a very simple tight bind model, putting a single orbital in each of these adjacent atoms of a vacancy, and we can have a lot of different local geometries, but this is something simple to construct. And we have a hopping between adjacent sites, which is this term here, but we can also do it to the non-symmetric spherically symmetric vacancy, and spin orbit coupling. So when we include these two terms, we have something that it's very known from the textbook, that we can have double degeneracy states. So in the left side here, I'm showing the eigenvalues of these simple idealized molecules without spin orb coupling, the red dots is because there are double degeneracy states. So we have for a local environment of 3 atoms, 4 atoms, and so on. And if you turn on the spin-orbit coupling, this degeneracy is broken. So we have a gap between these two states. Okay, so let's now introduce an interaction between adjacent vacancies. So when you do this, there is another term in this Hamiltonian, and you can actually have a blocked phase that depends on the system periodic geometry. But in the end, just to get a quick look at the system, in each of these terms of the Hamiltonian, we have a real part that depends on the hopping of the vacancy, but the inter-vacancy interaction, which is the 3 prime, and an imaginary term that depends on the spin-orbit coupling locally, but also on the interaction of adjacent vacancies. And if you play with this kind of system, so we have the real part and the imaginary part, and I'm calling this sin of phi, just to play with the signal. And here is a 3-dimensional plot, and every plane here is a kind of different local environment. For phi equals 0 means that there's no spin-orbit coupling, and we see some degeneracy states as I showed earlier. But when you play with this value, if it is positive, a gap opens, but if it's negative, a gap also opens, but I cannot connect these two regimes of gap without closing it at the degeneracy point. So that means that I cannot adiabatically connect this regime of positive and negative phi without breaking this property. And as this term here depends on the inter-vacancy interaction, this tells us that we may have a regime that a topological transition can occur. So to answer this question, can a vacancy induce band inversion? Yes, it's possible. So now we have the ingredients. We can now actually start to look at materials to find some that has this property. So that's what we did. So we take a lot of different materials, induce defects in them, and look if they are topological or not. So in the ingredients that we find is that we need to identify that they have in-gap states associated with the vacancy, see if there is some spin-orbit coupling induced split, and then tune the vacancy concentration to see if there is a topological transition. So we start with the C2DB database. We filter some non-magnetic trivial insulators with a certain value of gap and select 308 binary materials. We calculate vacancy formation energy for all these materials, check if they have in-gap defect states, and look for the spin-orbit coupling splitting, and they actually end up filtering 179 materials that may have a certain vacancy density that can lead to a topological transition. And if you combine these 179 materials, because they have possible different vacancy sites, there's a combination of more than the number of materials, of course, that can be candidates to have a topology driven by defects. So instead of showing all of these materials, I will show just a class of them, which is interest of the experimental groups here in CNPEM, which is the transition metal dechalcogenide, which is interesting because there's a lot of experimental analysis methods to manipulate defects in these systems. So here we have just a summary of some of what we have done. So we calculated the vacancy formation energy, both for the transition metal, but also for the chalcogenide side. And the chalcogenide's formation energy, vacancy formation energy is way lower. And that says to us that it's more probable to have this kind of vacancy. This is the wave function of this defect state. So when we make a chalcogen vacancy, what happens is that there are pure localized states in the system gap, and these states, of course, if we project in the real space, they're localized around the vacancy site and have this kind of symmetric triangular hypothesis that I showed earlier. And of course, we actually see that there's a spin arc splitting all this material, so we have computed for all the 1T more stable phase of transition method chalcogenide, but also for the 1H phase, the MOX2. And of course, the higher atomic number atoms, platinum and tungsten, has a higher spin arc coupling splitting, and as we will see, this seems to be a good idea for topological insulator, but it's not in this case. And here we also have that the states are very localized. So it's something that can influence also the topology, because it depends on the intervacancy interaction. And also these vacancies likes to be in a certain configuration. They prefer to be across each other on the bond. So this may favor a higher density of vacancy, and experimental results actually show that there is a self-assembly of this vacancy in a higher concentration, which can lead to the topological phase that we will show. And I need now to show to you guys that this material is indeed topological. So we have done some DFT calculation for the band structure, which is this blue dots, but we can actually understand very simply these defect states by the sort of tight binding model that I showed earlier. So we can extract these parameters and understand the physics behind it. So we have the first enable intervacancy hopping, the intervacancy hopping, and also the spin arc coupling in this case. And we can see that if we start from the higher vacancy density, the system has a gap, and this indeed is topological. This is a ribbon of this material showing the topological add states. Of course, if you diminish the number of vacancies, the gap closes and reopens again in a trivial phase. So the system, there is a topological transition depending on the vacancy concentration. And this is all done by this simple model. We can construct this phase diagram that depends on the spin arc coupling, and alpha here is a measurement of the intervacancy interaction here. So what tells us is that if you have a higher spin arc coupling, you need a larger vacancy concentration to achieve a non-trivial phase, which is counterintuitive, because when you look to topological insulators, usually we are looking for heavy atomic number materials that has a large spin arc coupling. And this red dot here is the full DFT calculation of the topological invariant using Wernier function for a different supercell analysis of a vacancy. So the 3x3 has a higher vacancy concentration than the 5x5, and we see actually this topological transition. So this is just a summary of what I showed until now. So we can have this topological transition, and all things seems to be beautiful in transition method chalcogenide, which is a very studied material. But also, if you look here, you may kind of be scared because the vacancy concentration seems to be very high. So 10 to the power of 13. If it was a three-dimensional semiconductor, this would be 10 to the power of 21, which is kind of scary. But a lot of experimental results show that the vacancy concentration are naturally occurring at this concentration in a lot of materials. And okay, but this just shows that it do not need to be well organized. The vacancy, if you have a random distribution, we can actually also find a topological transition. And this is the final picture of this part. That we have the topological transition in this kind of interesting material, but this is a Brazilian expression, not all is flowers, nem tudo é flores. The topological gap is above the Fermi energy. So we actually need to dope this material to get to this interesting topological phase. And that may be a problem. Why is that? It's because I need to incorporate more electrons in the system, and as these vacancy states are localized, the electron-electron interaction may actually screw up our topology. So in this discussion arise also from a recent paper of the group of Andrei Bernevik that classify many materials as being topological when he relaxed this condition that he is not looking only at the Fermi energy, but allowing to check the topology for unoccupied states. So this raises a question over this unoccupied topological states that we are called from now on virtual topological insulators. They are still robust or not. So first, just to show that in principle it's possible to occupy these vacancy states, we can construct an interface with aluminum, and we actually need to apply an external electric field. We can actually occupy these states, but this -2 vacancy state, it's not stable within the gap of the semiconductor. So there's when you occupy this extra band here, they actually become resonant with the material conduction band. But nevertheless, we can still calculate if the topological state is robust. So that's our goal here. We want to check if this gap here is indeed robust or no by increasing the electron-electron interaction. So we did this, extract the parameters for different transition methodological cogenide, and what we include now in the model is the electron-electron Hubbard-like repulsion in a mean field way. And so just to show simply what this repulsion does to these energy levels, the spin-orb coupling. So this is getting back again to the simple three-site model. We have three eigenstates for this idealized molecule, and the spin-orb coupling separate a gap here from these states and separate it linearly. And the electron-electron repulsion also does this linear when the spin-orb coupling is 0. So in the middle panel here, I'm showing the energy gap between those two states. And when you have these two terms competing with each other, we have a kind of square root of square of the components. So they can actually increase this gap here, and that we show earlier. If you have a larger initial gap, we need to have larger vacancy interaction to drive a topology. So this is just a summary. I take a particular case, and this is the system without electron-electron repulsion, and for a very low vacancy concentration. So this state is in a trivial configuration. This side panel here shows the spin-Hall conductivity calculated by the Kubo formula. When you increase the vacancy concentration, eventually you have a topological transition, and now there is a quantized conductivity. And if you start with this topological case now and increase the electron-electron repulsion, it can actually lead back to a trivial phase. So the gap closes and the conductivity is not quantized anymore. So just a summary of this phase diagram, now plotting the vacancy concentration by the electron-electron repulsion. So this is for the virtual topological insulator, where I have only 2 electrons in this vacancy. And this is for the real topological insulator. When I put 2 extra electrons, actually the Fermi level are now in the topological gap. So does not seem to be very different, but if I subtract these two phase diagram, we see that there's a lot of region in this phase diagram, that the virtual topological state exists, but the real do not exist. That means that if I occupy that gap, the system is no longer topological. So that's something that we need to take care about when trying to look at topology, not on the Fermi energy, not on the ground state of the material. So this is just the take-home message from this work. So we can actually manipulate the defects in two-dimensional systems and drive topological phase. And this is useful because this is something that is done in a lot of different contexts in materials, say for catalysis and other areas. And you can actually induce a region with vacancy and lead to topological state. But there is an interplay between we need a system with not so great spin-arb coupling and higher vacancy concentration, and not so great also electron-electron repulsion. So these red curves here actually map this gap, which we derived theoretically, and well, that's it. Thank you, everyone.
Thank you, Felipe. We're open for questions.
Very nice, Felipe. So, can you comment whether this feature can also happen in other two-dimensional materials? So, do you think this is a universal feature, or what would be needed for it to work in other 2D materials? Can you comment on that?
Yeah. So that's something that we are looking at, and for these other two-dimensional materials that we have explored, we not computed the topological invariant for all of them, but to at least 30, there's still a topology present. So this is something that can be applied in other contexts as well. So what depends in the end is that not only this local environment for the vacancy, which is important, but the type of orbital that is formed here, if there are d orbitals or p orbitals, and actually the geometry. So when you go to random vacancies, there's something more to it than look only to the spin-orb coupling in the vacancy interaction.
Thank you for the presentation. I have a different question, but I want to follow up on this one. So let's say the same orbitals involved, for different materials, the range of hoppings or interaction terms that you have are in the feasible range in reality, or do you need a huge concentration of defects for this to realize?
Yeah, so particularly for the transition method chalcogenide, which we have actually compared with the experimental literature,
Yeah.
we are within the experimental range of vacancy values.
For the whole family of TMDs?
Yeah, so some TMDs, when you do a lot of vacancies like this one, they go to amorphization, so maybe not of the TMDs, but for MOS2 and platinum diselenide, this is true.
Okay. So my original question is connected to this. How your conclusions would change if you include structural distortions, because you have a fixed tight binding model, but once you allow to relaxations, how these numbers change?
Yeah, although I have a fixed tight binding model, it was parameterized by a completely relaxed DFT model. So they have actually a very similar dispersion. So in the end, I maybe capture some of this distortion here in this parameter, but yeah, maybe some system that have some more abrupt structural change, and this will not capture.
In your parameterization, you changed the distances between T and T prime in the calculations?
Yeah.
With relaxations?
Yeah, the DFT code is done with fully relaxed system. So we have a
defects close to each other.
Defects
so
close and
nice.
far to each other.
Thank you.
Thank you for the presentation. I was thinking about when you introduce vacancies. Usually in these materials, the vacancies can be charged defects, but when you calculate your formation ends are neutral.
Yeah.
So how do you expect this charged defects can change the topology in this case?
So I'm calculating here. Yeah, you're right. So neutral vacancy defects, and actually for this system, which I can show here very quick. Well, this was not a good idea. We actually have done some calculation on the charged defects, and then within the gap, most of the range of energy, the vacancies is still neutral. When you need to do is to put extra 2 electrons, or you need to go to -2 state, and this -2 state is resonant with the conduction band. So again, the effect of one thing, it is possible to occupy this state from the without leaving the energy gap. So this is one question. The other is, when I occupy this vacancy, the system is still topological. So there's the electron-electron repulsion. So there's two parts of this answer. For the system, both are possible.
Okay. Thank you for the nice talking. Just a brief questions about relating the U term. How do you make this to parameterize this U term for the whole quantity of defects?
Yeah, so the U term here in our method is just, I did not fit from any ab initio calculation. I just varied in, let's say, by hand. So I vary a lot of values to see if the transition will still be present or not, but we have not estimated this value for realistic materials.
Okay, thank you.
Hey, thanks very much. Very nice talk. You mentioned at some point that in principle the topological state is stable against the disorder of the vacancies. I mean, this is somehow counterintuitive. At some point, the disorder should destroy the topological state. Can you give an explanation or a quantification how stable it is against disorder?
That's a very, very good question. So we have not deeply analyzed the impact of a larger disorder in those systems, but we have done some very simple calculations, randomized the vacancies, a very small cells, not a too huge cell, and we can still find some gaps that are topological. So we did not did a very extensive analysis, but at least some of these calculations have shown the vacancies to be, this system to still be topological.
Thanks.
Any more questions? Oh.
Thanks for the nice talk. I want to know, just a comment, if you know, how the Berry phase will change with the disorder, and if you calculate the Berry phase to see the topological transition.
So that's something that maybe follow the last question, and so we do not made a systematic analysis of how these wave functions are changing when we have a large ordered state and go to a disordered state, but of course when you have a lot of disorder, you know from the Anderson topological insulator that we may go towards a trivial phase, but here at least for this very specific vacancy concentration, the disorder do not play a role in the transition.
Okay, and for different models like BHZ model, this transition is observed with the, or just for tight binding that we presented?
Yeah, so we validated all this tight binding analysis with DFT calculation, so it's still feasible.
Okay, thanks.
No. So the discussion is, if you have a disordered system your Brillouin zone collapse to gamma. In that case, how do you define your Z2?
Yeah, so that's a good question. So there's other invariants that can be calculated for this larger or a non-periodic system. For instance, a bot index is one of them, but there's a lot of real space invariants that can be calculated. So here we focus on periodic systems. So we still use the Z2 invariant. Actually, we calculate the spin chart number, but yeah, there's some other invariants.
Okay, so we stop here, and we thank Felipe and Lucas for this very nice session. And we go for the coffee break and return at 4:20. 10? Oh, sorry, 4:10.
Eu acho que é 4:10. Ah, verdade. São 20 minutos de coffee break. Tá bom. Beleza. Aí agora eu fico de chair na última. Beleza, daí eu vou lá. Elon, levanta lá fora para mim. The next session will be starting, so I invite you all to come inside. The session will be starting now, so please come to the auditorium. Hã? Ah, vixe, bom, depois vai ser Vou segurar um pouquinho. Okay, so good afternoon. I will be sharing this session, and the session will be only one talk of Luis Felipe Pereira. Luis Felipe Pereira is a professor at the Federal University of Pernambuco, and he will be talking to us about computing latest thermal conductivity of a GST with neural network potentials, molecular dynamics, and Wigner transport equation. So, Felipe, you can start the talk.
Good afternoon, everybody. Of course, I would like to thank the organizers. It's a great thing that Luana and Mariana had this extra money to host us in this event. Let's see how long it's going to take before I start talking on the pointer and pointing with the microphone. So I'm not going to tell you, everything I've done before I got here, but the title got a bit long. And the story is that this work actually is a product of, a sabbatical year that I took, essentially, with a very generous funding from the INCT for Materials Informatics, for which I'm also very grateful. And the thing is, I had been working on molecular dynamics simulations of thermal transport, essentially calculating lattice thermal conductivities of several nanomaterials and other things, but mostly based on carbon and silicon, things that are harmonic and fairly well behaved. And it was time to learn something new. So I wanted to learn how to compute these things with essentially the Boltzmann equation, but then something better came or appeared along the way. And then that's how this story started. So I took a sabbatical to go to the University of Rome, and Francesco Mario was my host there. And then he had worked with a former student, Michele Simoncelli, was also actually a student of Nicola Mazzari, but they had worked together on this theory, which is particularly useful for anharmonic materials. So we had to find something to work that wasn't carbon or silicon or the things that I was already working with. And then Riccardo Mazzarello is also a professor in the physics department of Sapienza, and he's an expert in phase change materials. And at the time, he was collaborating with Marco Benasconi and Omar, who was a student of Marco in Milan, on GST, and that's how this whole thing got together. So we decided to employ these methods. First, molecular dynamics, which I already knew, so reasonably well, and then use the material to learn how to do the Wigner transport. So the general idea is that we have these phase change materials. They are useful for non-volatile memory devices and data storage. They were very used for rewritable, CDs and DVDs, which are not very useful today, or perhaps anymore. But there are other types of memory devices in which they are still important. And the idea is that you have, an amorphous phase and one or more crystalline phases, and they have some difference in resistivity or reflectivity or something like that. There's some physical property that changes a lot when they change phase. And the way to make them change phase is by Joule heating. So the thermal transfer properties of these materials are quite important. In the case of germanium antimony telluride, we have the most stable hexagonal phase. Then you have a sort of metastable cubic phase and an amorphous phase. Now, the thermal conductivity of the hexagonal and the cubic phase, the crystalline ones, is fairly well understood, and it can be described with the traditional Boltzmann equation or particle phase methods. However, for the amorphous phase, the thing was a bit more complicated, as it usually is for disordered materials. There was this work from 21 where they used ab initio molecular dynamics to compute the thermal conductivity of GST, the G2SB2T5, and GET4 in the amorphous phases. And then the way you do this kind of simulation, I'm going to talk a bit more later on, is that you perform several calculations on systems of increasing size and then you extrapolate with some heuristic equation, and what they got was this 0.26 watts per meter Kelvin. So it's something quite low, like the kind of things that Christian was talking this morning. And there are also experiments. So some very high precision, sophisticated experiment came out in 23, where they measured the thermal conductivity for the hexagonal phase, the cubic phase, and the amorphous phase. And then at 300K, which where these simulations were performed, they have something that was more like 0.2 watts per meter Kelvin. I mean, it's a small difference, but it shouldn't be there. And also, if you look at the calculations, the actual maximum, the largest system that they actually simulated was just below this 0.2. So it could be very well that, of course, this extrapolation is simply nonsense, or maybe just not good enough. So this was one of the things that got us interested in this stuff. And we thought, okay, maybe we should work on that. Of course, the point that, why people didn't just do larger systems with DFT or ab initio MD is that they couldn't, right? They were already at the limit of what could be done at that point in a decent amount of time. So we decided to, this is the type of stuff where you can use neural network potentials or machine learning potentials in general. And the idea is that to model these disordered and amorphous phases, you need the systems that are often quite large, and you need to do the simulations for very long times, which is just out of reach for ab initio methods. And then neural network potentials are perhaps the most flexible approach within the realm of machine learning potentials or machine learning models, because constructing and training them is relatively straightforward. And they are nonetheless a significant advantage over empirical potentials and cost a fraction of ab initio methods. Of course, neural networks can interpolate any sort of arbitrary nonlinear mathematical functions with a large number of parameters, even from a limited set of data, as many other speakers already mentioned here. And typically you have an input layer, one or more hidden layers, so that's the difference between a shallow and a deep neural network. And you have all these nodes interconnected by weights. So when I was preparing the talk, I was thinking of the students as well. I guess there are a few students. I can show a little bit of how these things are done, right? So in the training, the weights are adjusted to minimize some sort of loss function. So you use back propagation and typically some sort of gradient-based method to adjust the weights. This could be a typical neural network, right? With all this is my hidden layer with the nodes here. They have a bias, input layer, output layer. And we can simply calculate the value of each node based on the input and the weights. You have an activating function to compute the output, and you have a loss function. In this case here, the mean square difference. You do this until, of course, the loss is 0, which never happens, or shouldn't happen anyway. And you do it at a given number of iterations. And then you correct the weights based on this derivative and the learning rate to get to what you want. We can do this training. So this would be like Lerner-Jones. This is my initial guess, which are random weights. And this would be the data from a Lerner-Jones potential based on distance. I can do a simple network there, 1, 10, 1. So 10 nodes in the hidden layer. I can make something more interesting. I can put some noise, of course, on my Lerner-Jones data. That's just some random noise that I'm putting there. And this is my loss function. So I'm doing a very, very simple network with a very, very simple training data set. And that's actually where people started, right? So yesterday I asked Gabriel if he knew what would be the first paper on this kind of stuff. And I'm not saying that it's certainly this one, but it was the first one that I found, or the oldest one that I found, from 95. And it's very interesting. So they used exactly this type of neural network, and they trained it first on data from an empirical potential to model absorption of CO or carbon monoxide on nickel, on a nickel surface. And then they use some DFT data for the absorption of H2 on a silicon surface. And the interesting thing is that for the case of the empirical potential, they got a precision, or a mean average error in the energy on the orders of hundreds of kilocalorie per mole, so 0.0 something. And then relative to DFT, 2 kilocalorie per mole. So this is twice chemical accuracy, but it's not that bad actually for what they had at the time. And this is their neural network. So it was just one hidden layer. The input layer had essentially the distance of the molecule relative to the surface and some sort of orientation angle. And this was, the main work that I knew from 95 until the work of Belle and Parinello, where they introduced the descriptors. So those people didn't have; they were really using just positions and angles. Introduced the descriptors, and then you have one layer. You had one neural network for each atom, and then you put them all together to compute the total energy. And then in 18 came the work of Roberto K. and collaborators with the deep potential, right, which was essentially an improvement on the Belle-Parinello model. And however, the interesting thing is that at this point, right, so 2018, the mean squared error for the deep potential is essentially 0, right, relative to DFT. Of course, if you do it very well, training very well, as they did for water in this case, and you had this linear scale comparable to to much simpler potentials like TP3. In 2021, another type of neural network potential showed up. They're called neural evolution machine learning potential. And the idea here is actually go back again to something simpler. So NAP only has a neural network with only one hidden layer. So the expression for the energy is quite simple. You only have weights from the input layer to the hidden layer, and then the output layer, simple activation function, and the biases. And the amazing thing is that its accuracy is comparable to the major players in the neural networks, or actually machine learning potential. So GAP, which is not a neural network, the moment tensor potential, which is also not a neural network, the deep potential, which is a deep neural network, and NAP is a shallow neural network. Now the focus of NAP was actually not only accuracy, but also speed. So if you look at this comparison here for PBT or silicon, it's essentially twice as fast as the deep potential. The comparison with GAP and moment tensor potential is a bit unfair here because you're comparing stuff running on GPUs to CPUs, but still, if you run them on the same type of architecture, it's still considerably faster. The development of NAP continues. So late last year, this paper showed up where they have a sort of, it's not, I wouldn't say universal potential, but it's for, it's model for 16 elemental metals and alloys of those materials. But a couple of months ago, there was this preprint on the archive where they are presenting the first sort of universal neuroevolution potential for inorganic and organic materials. So they really tested this on all the data sets they could put their hands on. So many of those which are on the math bench that Gabriel also mentioned yesterday. Okay, so, but before that, I also, we had to train our own potentials. So the story was that Ricardo spoke with Marco and Omar, who were training a deep potential for GST to look specifically into crystallization. So they had a lot of different structures, so the cubic phase, the hexagonal phase, the amorphous phase, but they also had stuff like liquid, superliquid, quenched configurations, and metadynamics, about 200,000 configurations, all with a maximum of 108 atoms, so all sorts of temperatures. And their potential is quite good. So they had 5 hidden layers. They're trained on energy forces and virios, which actually it's optional, but they did it anyway. And they had, average, decent root mean square errors for energy and forces. The problem is that their potential has some non-linearities when you look at the small displacements in the forces. So here what I'm doing is I'm taking one atom from the amorphous supercell, let's say, and I'm displacing it by very small displacements up to 0.05 angstrom. And you see the forces should be linear or not, and then the force constants, which are the derivative of these guys, are not very constant at all. And this is really bad if you want to compute phonon properties from finite atomic displacements. We did show this stuff to them, and they managed to improve the potential using the attention mechanism in the training. However, this made the potential a lot more expensive. In the meantime, you know, I knew about NAP, and I thought, well, what if I take their data set and train NAP for this material? That's exactly what I did. I defined a radial cutoff of 7 angstrom and an angular 6 angstroms. That's essentially the same that they used. And I trained these on a gaming GPU that I have on my lab for 100,000 generations. Of course, if I continue here, I just see this thing, the loss function gets stable. We can look at comparison between predicted energies from NAP and DFT, forces, and the virials, which are particularly important for computing the thermal conductivity. Yeah, you know, you're going to look at this here and say, oh, that's not very good. However, these are the type of structures which don't really show up in my simulations, which are only for the amorphous phase. So I don't worry about those guys. There wouldn't be a problem for me, but there would be certainly a problem if you're trying to model crystallization or something like that. And then if I look at the force constants with my potential, I don't have any major problems. Okay, there's some issue here, but that's quite small. We're taking averages from positive and negative displacements anyways. In terms of performance, right? So I did a quick test on this this laptop here, but I've tested this also, of course, on the big clusters. We can use lamps. For the deep potential, we use this package, and for NAP, there is a NAP package as well for that runs on CPUs, on lamps, and so NAP is 40 times faster than the first deep potential that they had trained, which wasn't really quite right for what I needed, and it's 200 times faster than the correct one. So this is game changing really. And the point is that I couldn't do the molecular dynamic simulations that I would have to do, particularly with the corrected potential, but I could do with NAP without any major problems. Okay, so let's go into the molecular dynamics part and and lattice dynamics. So when we think of computing thermal conductivity, there are essentially two main methodologies: molecular dynamics and lattice dynamics. In molecular dynamics, I'm essentially talking about classical molecular dynamics. So we have classical mode populations, maybe not necessarily phonons, but I have all anharmonicities, as Christian mentioned this morning. We can do equilibrium molecular dynamics without a temperature gradient, right? So the whole system is at the same temperature. There is Green-Kubo, but there is also Helfand-Einstein and a spectral method. We can do non-equilibrium simulations where I impose a temperature gradient on the system, and there's a direct and a reverse way of doing this. And there is this so-called homogeneous non-equilibrium MD, which is something quite interesting, where you don't really have a temperature gradient, but you have something that plays the role of a temperature gradient. We go to the lattice dynamics methods. Of course, we get for free the quantum populations. And then you have the Allen-Feldman model, which is an old tested model for amorphous materials. It's fully harmonic, essentially. And then you have the partially unharmonic models, Boltzmann, Wigner, and the quasi-harmonic Green-Kubo, which is essentially the same thing. So these two groups develop things independently. And they are mostly Italian-based as well, curiously. But and they should give the same results. It's just curious that I happen to be on one group, but I had worked with the other people before. Anyhow, so for the heat current, we use this expression There was some debate a few years ago on what kind of expression was the correct one. We have all this development on this paper, and as Christian mentioned also this morning, like the calculation of this term is particularly tricky. In particular, the expression that is there on lamps for many of the many body potentials is not quite right, but for the deep potential it is, and for NAP it is as well. So we compute the thermal conductivity as an integral of this heat current correlation function, and since our material is isotropic, we can take an average. And then if you ever did this kind of stuff for a crystalline material, you would see the heat flux autocorrelation function decaying nicely to 0, and then its integral would converge very well behavedly. Unfortunately, that's not what happens here. The heat flux autocorrelation function is quite misbehaved, and then when we integrate it, we get a fairly large value essentially, but then what we want is this thing that is here that looks pretty much like noise. If I change the scale, I can look at this is just the integrated thermal conductivity as a function of time. So I have to do a 70 nanosecond, several 70 nanosecond runs, but I'm only looking at the correlation function to 10% of that time. So I can break this in 1 nanosecond intervals, and I take the average value of each of the last 5 nanosecond intervals to compute my thermal conductivity. This thing is extremely noisy, and it was a surprise for me, actually. I wasn't expecting that. There is the Helfand-Einstein method, which is quite interesting because if you we usually see this stuff on statistical mechanics classes or thermodynamic or something, it's the diffusion problem, right? So it's totally equivalent to the Green-Kubo formulation. Instead of computing the integral of the autocorrelation function, you take the time derivative of the mean square displacement of the quantity. So for the diffusion coefficient, it would be the correlation function of the velocity and then the mean square displacement in coordinate. In our case, instead of the heat flux autocorrelation function, we use the time derivative of the mean square displacement of this quantity, which is essentially as Christian mentioned this morning as well, the body center, right, of the energy. This method, it tends to be a bit less noisy in general. So this would be the mean square displacement for 4 samples in each one of the X, Y, and Z directions. And then if I average all the directions for each sample, and then I average all the 4 samples, I get this orange thing here, which looks a lot like a straight line. And then when I look at the conductivity, I still have the same issues. I still have a bit of noise. I have to break these into blocks, into 1 nanosecond blocks to take the average. If I put them side by side, the scales are the same, so you see that this is a lot noisier than this. But in the end, I get essentially the same results for the thermal conductivity, 0.172 or 5 plus or minus 0.005 watts per meter Kelvin. This uncertainty is the standard error of the mean calculated over the 5 boxes. There's another method which is a spectral method, and this one I also learned during this sabbatical. It's quite interesting, is that you take the heat flux autocorrelation function and then you take its Fourier transform, so you have the power spectrum, and then the 0 component of that power spectrum gives you the thermal conductivity. The problem is that the power spectrum looks like this gray thing here in the background. The blue one is a running average over a certain frequency interval. Now, what these people realized was that you could actually fit the data, so you define a maximum frequency as a cutoff, and then you perform a fitting to get the value of the 0 frequency component. Doing that, for GST, I got thermal conductivity of 0.18 plus or minus 0.02 watts per meter Kelvin. The uncertainty is a bit larger. It's not very useful in this material because it's quite noisy, but for things like silica and alumina, this works like a charm. You do a very short molecular dynamics run, and you get essentially the perfect number. In terms of non-equilibrium methods, so we actually now have a temperature gradient. I can heat up my material in the center and then cool it on the corner, so the heat flux goes to the sides. After a transient period, the heat flux stabilizes. I can actually measure the temperature gradient on the sample. I just divide it in regions and calculate the sort of local temperature. And then with that, I can compute the lattice thermal conductivity from Fourier law. That's essentially what those people did in the initial result that I showed. However, I could do a lot more sizes than they could. And the interesting thing is that after some time, indeed, the thermal conductivity seems to saturate around this 0.180 plus or minus 0.005. And this is the size where they got to with the ab initio MD. However, I still had a lot more atoms. So each point here, the first point has 2,000 atoms, the second one has 4,000, and so on and so forth. The last one there has almost 36,000 atoms. So it would be completely out of reach if I had to do that ab initio. Finally, there is this homogeneous non-equilibrium method in which we have a perturbing force. So this is a method that was proposed in the 80s, but it was revived also recently. And the idea is you end up with an expression that's very similar to the Fourier law. You have the heat flux divided by something that has the same dimensions as a temperature gradient. You have an external parameter that you have to control, but it's not hard to do. And then when we do that, so for different sizes here, the smallest cell size, 200 atoms, and up to 2,000 atoms, we get results that are all compatible. So if I put all of them together, we have Green-Kubo, Helfand-Einstein, the spectral method, the reverse non-equilibrium method, and homogeneous non-equilibrium method. And they give something in this range between 0.167 and 185. So now we are below the experimental value, whereas the initial values were a bit higher. However, something that also came up last year was this paper where it seems that NEP has a tendency to undervalue the thermal conductivity. So perhaps that's not our fault. And then we can move on to the phonon or particle-based methods. First, the Allen-Feldman model. We have a conductivity that is computed from phonon frequencies, specific heat, and the velocity operator. And then you have this delta function here. So what happens is that essentially you should get, this thing should have a finite thermal conductivity only if two modes have exactly the same frequency, or they interact. Otherwise, the system is completely harmonic and they don't interact at all. So to get something that is physically sensible, you have to broaden all the phonon peaks, essentially. So you add an extra term here to your delta function. You're broadening the delta functions. It could be a Gaussian broadening or Lorentzian broadening. It doesn't really matter that much. And then what you see is the thermal conductivity as a function of this broadening. The idea is that there should be a range of values for this broadening for which the thermal conductivity is constant. It doesn't depend on the broadening itself. And then that's essentially what we have here in this area. So I have here for the calculation for 2,000 atoms at 300 Kelvin or at 1,000 Kelvin. You see there's no major change. However, there's something interesting here, which is the following. At the beginning, or at least at the region where this thermal conductivity for the Allen-Feldman, or prediction from the Allen-Feldman model is constant, right? It's below molecular dynamics. So it's very strange. You're taking a fully harmonic model, and it has a thermal conductivity that is lower than the molecular dynamics, which is fully unharmonic. Now, the conclusion that we can take from this is that in this material, of course, the anharmonicity is increasing the thermal conductivity. For a crystal, this would be nonsense, right? But for amorphous materials, it can actually happen. Now, the Wigner model, which was developed by Simoncelli, Mazzari, and Mauri, is essentially a modification or sort of extension of the Allen-Feldman model where they replace that delta function by actually a Lorentzian with a full width at half maximum that is given by the average line widths of the phonon modes involved. So with that, you have a properly anharmonic model. you can break down the thermal conductivity between a contribution from particles and from things that are not particles. They called coherences. So, you know, all sorts of wave-like things, locons, vibrons, and etc. And the idea is the following, right? So the Wigner describes heat transport within this phonon sort of particle-like picture from one extreme to the other. So you have simple crystals, where you have, you know, Boltzmann, pi of Boltzmann works really well. You have disordered materials like glasses, where wave-like tunneling is the relevant quantity. So here Wigner extends the Allen-Feldman model. And you have the intermediate phase as well, where you have a very complex material where you have both particle and wave-like transport simultaneously competing somehow. Okay, so in order to actually use that, we have to compute the line weights of the phonons to put there. We computed that considering only 3 phonon scattering, you know, in the relaxation time approximation in phonon 3 pi. And I actually did the calculation initially for even smaller cell than I was using before, just 81 atoms using a Fourier interpolation, or for 216 atoms, but only at the gamma point. And then at 2 different temperatures, you see, of course, the line weights increase, so the system becomes more anharmonic. There's no big deal there. But then when we compute the thermal conductivity so this is using, the lower one is Allen-Feldman, and the upper one is Wigner. In the low temperature regime here, they give the same result. But what is interesting is that, so for Allen-Feldman, there is a sort of size dependence, and there is an open discussion if the Allen-Feldman model really should give you a finite thermal conductivity, or if you only get that because your amorphous models are finite. But so I don't want to get into that discussion. However, the Wigner results, you can see they all bunch up here, and there is no clear dependence, and it's not size dependence, not increasing or decreasing as I increase the system size from 81 atoms to 4,000. Okay, so when we put all of these things together, we get the Wigner result is 0.166, is just below that that MD result, but we can do one more step. I can ask myself, okay, so this difference, which is insignificant at this point, between Wigner and the molecular dynamics, is it due to the neglect of higher order scattering, phonon scatterings in my calculations, or is it just due to classical phonon populations? Checking for the second one is considerably easier. I just have to go into the code and change the calculations of the specific heat, and that's exactly what I did here. So the black line is the correct Wigner result. The blue line is the correct Allen-Feldman result. And then I have here the calculations from homogeneous non-equilibrium MD at a bunch of temperatures. And you see in the higher temperature regime, they tend to equalize, but for lower temperatures, they're different. However, what the people who do molecular dynamics usually do is to quantum correct our conductivity. But here I did the opposite. I quantum corrected between quotation marks, or classically corrected perhaps, the quantum result. So I changed the specific heat to a classical expression, but I leave the quantum specific heat in the computation of the line weights, or I can actually use the classical specific heat to calculate the CV itself, and also in the calculation of the line weights. And then we get this perfect agreement here between molecular dynamics and Wigner. So let me just conclude this by saying that, so the one thing interesting that we found that we didn't really expect, however, it's not something so intuitive, is that the anharmonicity is actually increasing the thermal conductivity of this material. Something that was very refreshing for me, also because, so I started working on thermal transport on graphene in sort of 2010. And at that time, if you looked into the literature, there were the results for the thermal conductivity of graphene computed by molecular dynamics were anything between 100 and 10,000 watts per meter Kelvin. And I never thought that it was acceptable. And people would say, oh, but I use a different method. I use a different potential. Well, I use a different thermostat. That's not good enough. We did a lot of work, and we showed that actually if you used all the methods correctly, you should get the same result. And again, we're doing this for GST here. Another interesting thing, of course, was that actually molecular dynamics and Wigner give you the same result. And the point is that actually Wigner can be a lot cheaper than molecular dynamics, even with the neural network potentials, particularly because you can do much smaller systems. And so once we got that, I went back and did all the calculations with the DeepMD potential, or the deep potential properly. Just for the Wigner, I couldn't do molecular dynamics with that. And the result that we get is like 10% higher than that. So pretty much the experimental results that we had there. Okay, I guess that's what I wanted to say. Thank you.
Questions? Thank you, Felipe. Very nice talk. I'm curious, how can you get thermal conductivities in the Allen-Feldman method if it has only harmonic quantities, as far as I understood? So where's the trick?
The trick is this arbitrary broadening of this delta function. So if you don't have it, if you do a calculation at the gamma point, you get zero conductivity. If you do a proper calculation with Fourier interpolation, you get an infinite conductivity. So the point is, if you had a system that was, so if you look here, this is the black curve for 200 atoms and the red curve for 2,000 atoms. If I did 20,000 atoms, this guy would be even higher up here, and eventually it would invert. So since I don't want to do a calculation with 200,000 atoms, I can simply use Fourier interpolation to get equivalent. How do I choose the eta? Exactly. So you should have something that's called a convergence plateau. You won't have it for very small systems, but for large enough, you would see that. So this is a log scale, right? I change eta from 0.2 inverse centimeter to 2, say, and the conductivity changed by 10 to minus 3. So if I even go to an even larger system, this would be even clearer. However, this system is really a mess to work with. If you do this on silica or alumina, the plateau is really clearly visible, even for smaller systems.
Thank you for the talk. Very interesting here on the back. You put on your last slide something like that is a question, right? You left it there. So why the new deep potential? What it changes in the potential itself that you redid the calculations and now it's 10% higher than in your conclusions you showed?
No.
Now
so
you redid.
The point is, whatever I got with the first version of the deep potential was wrong.
Yes.
Because the force constants are wrong, right? So what I'm saying is that if I can't do molecular dynamics with the correct deep potential, because it just takes too long.
It's not that one.
Sorry?
No, it's not that one, the corrected.
Yeah. But then I can use the correct one to compute the thermal conductivity with the Wigner method, which based on my NAP results, I know reproduce the molecular dynamics results as well.
Okay.
Right? So I know that I'm not missing any fundamental unharmonicity on it.
But do you conclude something like the deep is better for you, or
it's more precise? Yes, it gives me the experimental result essentially.
So with this Wigner method now, you will not use NAP anymore. Is that a conclusion?
Oh, I see. No, I wouldn't say that. That deep potential was trained by people who've been doing this for 30 years. And my NAP potential has been trained by a guy who had been doing that for 2 weeks, right?
Okay.
So I trust my results. I think, I trust them, but because I can compare directly to high quality experiments. I wouldn't really, trust them if I didn't know the right answer to begin with.
Thank you.
But I would trust any potential fitted by Marco Bernasconi anytime.
So we have time for one more question. No more questions? Okay.
I mean, you mentioned that in the Allen-Feldman you're looking for a constant, I think the parameter was eta. What is the logic behind it? If you compare it to the Wigner transport, the broadness eta should actually be your finite line width, and that is driven some material-dependent constant that describes your line width of the phonon spectral function. So why do you try to reach a stable minimum there? What is the relation to the...
It's not really me. That's how Allen and Feldman originally proposed it. No, so the idea behind it is it's some sort of convergence essentially, right? So you know one limit. So eta is 0, the thermal conductivity should be infinite because the system is completely harmonic, right? So what they argue is that, okay, so you increase this thing because there is a lower bound for it, which is 0. You start increasing it, and then it's going to change your conductivity. It's going to do something to it. Okay, if it's infinite, it has to go down, right? So it's also upper bounded. The point that they make is that there should be a range of values of eta in which the conductivity doesn't change, which is constant. And then they say, okay, so this is the right value. I agree with you. It's not clear to me why that should be the right value.
I mean, it's more of a lower bound, is it?
For a crystalline material, it would be an upper bound. For an amorphous material, it could actually be a lower bound, as we found for this material particular.
Thanks.
So let's thank Luis Felipe again. So now we should go to the visit to Sirius. So I would just, we can go by there. Okay, so just wait outside, people, the ones that are going to visit Sirius, and then we'll send you the instructions there, okay?